Welcome to the TOEFL Listening section. In this section, you will listen to an academic lecture and then answer questions about what you heard. You may take notes while you listen. You will have time to review your notes before answering the questions. Listen to part of a lecture in a university class. You will hear the lecture only once, so listen carefully. After the lecture, you will answer some questions about what you heard. Some questions ask about the main ideas and supporting details. Other questions ask you to make inferences or connections between ideas. Answer each question based on what is stated or implied in the lecture.
Good morning. Today we examine particle wave duality and the double-slit experiment as the clearest illustration of quantum behavior that forces us to rethink what we mean by particle and wave. The phrase particle-wave duality refers to the experimental fact that entities such as electrons and photons show properties we would label as particle-like in some experiments and wave-like in others. This is not a metaphor, but an empirical observation supported by many experiments. Let us start with the classic double-slit setup. When a coherent beam of light or a beam of electrons passes through two narrow slits, and no information is available about which slit each quantum goes through, a pattern of alternating bright and dark fringes appears on a screen. These fringes are interference, and they are a hallmark of waves interfering constructively and destructively. Louis de Broglie proposed that every material particle has an associated wavelength that depends on its momentum. He suggested that the wavelength is Planck constant divided by the particle momentum. That de Broglie wavelength explains why electrons can produce diffraction patterns when they encounter a lattice or a slit that is comparable in size to that wavelength. A landmark experimental confirmation came from electron diffraction and the Davison-Germer experiment, which showed that electrons scattered from a crystal produce diffraction peaks just like X-rays. That experiment provided direct evidence that particles can show wave-like diffraction. A more striking demonstration is the single-particle double-slit experiment. When electrons are sent through the slits one at a time, single impacts appear on the detection screen as localized dots. Over time, these dots accumulate, and the familiar interference pattern emerges. The pattern builds up particle by particle, which tells us each electron behaves as a wave distributed in space until detected, and yet the detection event is localized like a particle. We explain this behavior using the concept of a probability amplitude or wave function. The wave function propagates through both slits, and its squared magnitude gives the probability distribution for where a detector will register a hit. Interference arises from the addition of amplitudes, not probabilities, so phases matter. An important caveat is the role of measurement, or which path information. If we place a detector to record which slit the particle went through, the interference fringes disappear, and we observe two single slit-like intensity distributions. In other words, acquiring path information forces the system to behave in a particle-like manner. This observation is often summarized by complementarity, which says that wave and particle aspects are mutually exclusive experimental descriptions. The availability of path information and the visibility of interference fringes are complementary. Contemporary experiments push these ideas further. Weak measurement techniques can extract limited path information while partially preserving interference fringes. Neutron interferometry and atom interferometers use matter wave interference for precision measurements of gravity and rotations. Electron microscopy relies on electron wave properties to resolve atomic scale structure, so the wave nature has practical consequences. We also see that coherence matters. If the source has very short coherence length, interference is washed out. Thermal sources or noisy lasers reduce visibility. Coherence time and coherence length are technical parameters that determine whether wave-like interference will be observable. To summarize, particle-wave duality is not a contradiction, but a statement about how quantum objects must be described. Depending on experimental arrangement and information available, they display wave-like interference or particle-like localization. The double-slit experiment encapsulates this duality and continues to inform both foundational questions and practical technologies.
Listen again to part of a lecture, then answer the question.
If we place a detector to record which slit the particle went through, the interference fringes disappear, and we observe two single slit-like intensity distributions.
This concludes the listening section. For more TOEFL practice tests and study materials, visit Spinta.org.